a message about the calibration problems we have in our laboratory. I am from Warsaw University of Technology, also program Warszawa, from Department of Mechatronics, Institute of Micromechanics and Photonics. And in our laboratory, this clean room lab, we are testing micro nanostructures, including also ultra-thin films with thickness between 5 nanometers up to 500 nanometers. And we are involved mainly in studies of nanomechanical properties of such structures, and also nanotribological properties, and also adhesive properties. So for this, we are using mainly atomic force microscope, and also nanoindentation, sometimes to compare the results from nanoindentation made with atomic force microscope and nanoindentation and so on. And the main problem we have still, in particular in friction studies, nanoscale, it is a calibration, of course. So it is the problem of nanometrology. And this area, I think, is a very special area and ignored completely, almost. NIST in Gatesburg, Washington, they are working something about this. They have a special, very expensive project, and so on. Also, it was a project in European project about some calibration structures using silicon, special components and so on. But it was helped, I think. So during our PhD thesis, we had a problem how to compare the nanoindentation test with nano-wear test. So what is the correlation between density of energy used for plastic deformation on nanoscale of the material with the density of energy which is used to remove the material on nanoscale? And we were working in the area about 25, 30 atomic layers in this space. So for this, it was necessary absolutely to calibrate exactly our atomic force microscope, because we wanted to exactly estimate the energy. So we were looking for good method for calibration of atomic force microscope in northern direction and also lateral direction. Because to estimate the friction energy which is introduced during nanowear test, it was absolutely necessary for us. And we studied many publications, many different sophisticated methods, probably you know some of them, for calibration atomic force cantilevers. And this method, they are inaccurate, very inaccurate in my opinion, and time-consuming also, very sophisticated. So my students started to think about a completely new approach to solve this problem. Because if you buy cantilevers, of course, so you have some force constant in wide range, because they are using typical silicon etching technology to fabricate these cantilevers. They can control exactly the dimensions of structures. So this is the outline of my talk, so I want to introduce something about this new calibration method. And what is important, my PhD student, after this hard work, organized, arranged a company, which is named Nanoidea in Polish, and Nanoidea in English. And this structure is here, so we can take this information material, of course, because it is under commercialization now. Very good exam, I think, also for you. Probably it will be better like this. So we can take, if you are interested in this material, and also look for this structure. I'm going to tell you something about this. Just one.
We can take it.
Yes, you can take. Please take this information material. And move around. So I will say about the origin. So something it was already spoken to you, but after that the calibration structure will be described and the use of calibrated atomic force cantilever to study in particular such structures like micromembranes used in microelectromechanical systems. There are many such components in such devices, and nanoelectromechanical systems. So very, very, very thin membranes, and with very small diameter, something like 100 micrometers or something like this, and in nanometer thick. So we have to identify stiffness in particular, mechanical characteristics, behavior. It's very important for calibration of such sensors sometimes and some other devices. Okay, so this is the origin of the studies. My PhD student was studying this problem, the comparison between nano-indentation and nanoware problems, some publications, and so on, and finally, this company again. And our approach was very simple, because we are using the approach of black box method. So we have some well-known normal force, so force generally speaking, applied to the system, to the cantilever, for example, and we have some change in arbitrary units. Usually it is voltage, from atomic force microscope. And what is inside? It is interesting what to put inside. And inside we are putting a spring, well-known stiffness. But the problem is what kind of spring we have to use, and what kind of material should be used, and so on. What should be the geometry of this spring, and so on, so on. Many different problems. And the idea of this calibration is such that if we have such spring with well-defined stiffness, calibrated exactly in our laboratory somewhere, so after that, if we make first experiments, force distance curve, you know probably what is this. So we are approaching our tip using scanner to our SEM. So this is the approaching, and this is the indentation after contact of the tip with the material. So if we know this, so we have relation something like this, because we have exactly displacement of the exoscanner, our tail would descend in that direction, vertical direction, and we have, of course, in arbitrary units, this force, because this is the distance and this is the force here. But the force is given in arbitrary units, electrical signal, of course. We don't know what is really the force, and we want to know this force. So firstly, we are doing experiment using our atomic force microscope on the cantilever. So we are doing something like force distance curve using very stiff material, like thin crystal silicon. It is okay for us. So we assume that there is no deformation in the contact area between the tip and our silicon cell. So by this way, we can identify the stiffness of the cantilever, but unfortunately we have arbitrary units. But we know the stiffness. Okay, and after that, if we have a spring with well-defined stiffness, so we are introducing this inside the system between the cantilever and the substrate, very stiff substrate, and we are doing also force distance curve. Again. And because we know the stiffness, and we know the deformation, because it is displacement of the scanner in vertical direction, so after that, with very simple equations, we can estimate exactly the stiffness of our cantilever. I will be not introducing you inside this detail because it will take some time. So it is not important, but this is the simple idea. You can see these equations. Okay, so I follow you. Okay. And what is important here, it is placement of the tip exactly in these structures. So after some sophisticated thinking, my students went to this idea to use a special membrane with different geometry. Sometimes it is very beautiful, a kind of art. And to produce these structures, we are using photolithography process and etching. And we are using beryllium bronze, because beryllium bronze has no hysteresis. Hysteresis is very important here. And we are using beryllium bronze foil with thickness about 30 micrometers or 50 micrometers. And using different geometry, we can control stiffness. From very low stiffness, 0.005 Newton per meter, up to 1,000 Newton per meter, depending on the geometry. Of course, and what is important, it is necessary to look how the system behaves during calibration when the tip is not contacting exactly in the center. And this structure were optimized in this sense. So there is some tolerate area that the tip can not be exactly in the center during calibration. And finite element method was used, modeling, and so on. So it was optimized by this way. Oh, you can see the results here, something like this. And after the different geometries, very beautiful sometimes. And also we tested the effect of geometry on the difference in stiffness. So the accuracy is very important for us, just to optimize the geometry in this sense, also for different stiffnesses. And you can see, of course, this is the big effect of the stiffness on the accuracy. It's a very normal problem in metrology, of course. So this problem was solved. So you can see that we are below 5%. And this method is very sophisticated. I were over 10, 20 usually percent in accuracy. Okay, and you can see geometry also, the effect of geometry here on this problem. And after that, it was elaborated also the special software. So you can purchase such structures together with special software for your atomic force microscope. And this procedure of calibration by this way will take you about 20 minutes. And this is the special system built for exact calibration of the structures in this company. Very brave student, really. He was doing, starting from zero, everything by himself. Mechanics, electronics, and so on. Software, okay. And after that, we are using these calibration structures to calibrate our atomic force microscope. We perform experiments with these micromembranes in these conditions. This is clean room lab. Temperature is type, humidity, and so on, and cleanness. And we tested different, we are using, for example, for this experiments with membranes, special cantilever with diamond tip. And very close, yeah. Okay, and we tested, for example, such membranes from the Fraunhofer Institute, and also another membrane from Tyndall Institute, from Cork Island, and so on and so on. That's very special membrane hanging from some plastic things. And what is important in this testing, that you, using this 4-distance curve in calibrated AFM, you can find the moment when the membrane is touching substrate. It's very important for practical application. So you can see this is 4-distance curve here, and also touching with the substrate, indentation, something like this, and coming back. This is pull-off force, of course, when the membrane is going up, and so on. And having this characteristic, it is possible to identify stiffness, of course, depending on the size, and so on and so on. And distance between membrane and the substrate. And pull-off force, of course, also. And also, we tested hysteresis of these membranes. So the time of loading was very long, and we were waiting. And we tested the hysteresis during approaching the tip to the membrane and coming back. So, and of course, this thickness was different, depending on the time of contact and so on. And this is the summary and conclusion. So we propose completely new method of calibration of AFM, and also nano indenters and force sensors and so on and so on. And I think that this method is very simple, and it can be used in many applications, in particular for identification of mechanical behavior of MEMS and NEMS structures, and also to solve, I think, we compare this calibration methods with different methods also. So it's absolutely a very, very precise method. And thank you very much for your attention.
Does anyone want to the talk? The talk is open for discussion.
Yes. One question. Thank you for very interesting as for me report. Also as for me, 135 nanometers, it is quite big radio for needle. Can you measure your forces of AFM with the needles of approximately the order of nanometers? Because it is very important to use such needles in order to, if you want to obtain resolution, in the order of nanometers. 135. We start our work with atomic force microscope about 10 years ago with such needles. Now we are working with 1 to 5 nanometer needles. So that's why my interests are quite special. Please.
I don't understand exactly what is the problem, because you are
in the
saying
end,
something about the tip, about the contact area.
In the end of your tip,
yes,
radio ought to be the order of nanometer. Can you produce measurement of force of atomic force microscope?
Of course, we tested the effect of the radius of the.
Do you have appropriate samples?
But for such experiments, we are not using very sharp tip. Because the very sharp tip is important for topography, for example.
But you need also to produce appropriate samples for measurement of such small diameter tips, yes?
Yes.
Yes. But it is practically it is possible.
Yes, it's no problem. Yes, we tested the effect of the contact and the formation and the contact area, of course.
It's very.
Yes.
We have time for another question, please.
How do you calibrate the size of indenter and the angle of indenter?
You mean the radius or the shape of the tip? So it is not. We tested using many different cantilevers with many different tips, with many different materials, and with starting from 5 nanometer radius up to special cantilevers up to some micrometers, for example, and so on. So we know exactly what is the effect of the geometry of the tip. We assume that the tip is absolutely stiff, practically. We can assume that it's absolutely stiff.
So let's to speak again.